And now we are going to do section 1 of chapter 15, Equilibria of Other Reaction Classes. So we're going to finish chapter 15 when we, after chapter 14. So in this lecture, we're just doing 15.1, precipitation and dissolution. This is the mineral fluorite, CaF2, and we can get this from a precipitation process. Pure fluorite is actually colorless, but really tiny bits of metals in the crystal give it that beautiful color. So sometimes from imperfection comes beauty. Okay, so in section 15.1, precipitation and dissolution, we're going to be writing chemical equations and equilibrium expressions representing solubility equilibria. And we are going to carry out equilibrium computations involving solubility, equilibrium expressions, and solute concentrations. So this is very similar to what we were talking about with chapter 13, which is why I wanted to do it here. There's a little bit of some different words and whatnot and different definitions, but a lot of overlap. We're talking about some other equilibria. So if you remember way back in Chem 2A, when we talked about solubility rules, and we talked about that there are some ionic compounds that don't dissolve in water that we call insoluble compounds, and we said they generally don't dissociate into ions when placed in water. If you had me last semester, you probably heard me say, well, technically, or I say we pretend they don't, or we assume they don't, and that's because in reality, they actually do dissolve to a small extent. And we call them sparingly soluble. Teeny tiny amount dissolves. So there's actually an equilibrium that is existing between the precipitate and its ions. For example, silver chloride going between silver plus and Cl minus. And it has this K that's way smaller than 1. But it actually is still there. There's a teeny tiny bit of silver and chloride ions. So this is just giving you a visual showing silver chloride as a sparingly ionic solid in water. Really tiny bit dissolves, giving us a very dilute solution of silver and chloride ions that are in equilibrium with the undissolved silver chloride. Here's another example, strontium chromate, SrCrO4. When we put this in water, it's going to split into Sr2 plus and CrO4 minus. And we have a new constant, a new equilibrium type constant, KSP, and SP stands for solubility product. So this is the K at when we have a solution that is saturated with dissolved ions. So this is the solubility product constant. So the first thing we are going to do here is write some dissolution equations and the solubility product expressions. So KSP is basically the same type of thing as KC. If you've got solids and liquids, we don't count them. So we mostly just look at the product side. Okay, because notice that our reactant side is all solids in general. So for instance, for this reaction, KSP, the solubility product, is equal to the concentration of Sr2 plus times CrO4 minus. Okay, very similar to KC. It's practically the same thing because SrCrO4 is 1. So let's start by doing some examples, starting with AgI, silver iodide, a solid with antiseptic properties. So we're going to say that AgI, solid, okay, it's back and forth between Ag plus, aqueous, and I minus aqueous. So you need to be able to look at it and figure out where your cation and anion are. So nice reminder of, what was this, chapter 2 or 3 or 4, something like that. So then our KSP is equal to Ag plus times I minus. The next one, calcium carbonate, the active ingredient in many over-the-counter chewable antacids. So when we see that split, it's going to split into calcium and then carbonate. So CaCO3 solid. And that's going to give us Ca2 plus. Remember, that's in group 2. And CO3 2 minus. Good old polyatomic ions. Don't forget about those. So that gives us KSP of Ca2 plus times CO3 2 minus. Our next one is magnesium hydroxide, giving us magnesium and OHs. Okay, and this is what's in milk of magnesia. So the magnesium hydroxide, magnesium is 2 plus. Again, like calcium, it's in group 2. Plus, we make 2 OH minuses. Remember, it's not OH2. They're each separate OHs. So the KSP here is going to be Mg2 plus times OH minus squared. Don't forget that coefficient, just like Kc. Next one, magnesium ammonium phosphate, which is pretty much insoluble, that we use to test for magnesium. So this is kind of an interesting one, right? Because it's actually going to split 3 ways. So MgNH4PO4 gives us Mg2 plus NH4 plus PO4 minus. And so KSP is going to be Mg2 plus times NH4 plus times PO4 2 minus. That should be 2 minus. There we go. Or 3 minus, sorry, not 2 minus. 3 minus. Sorry, that got really rough looking, but that's okay. All right. The mineral apatite, Ca5PO4 3OH, the source of phosphate for fertilizers. So Ca5PO4 3OH. That's going to give us 5 calcium 2 pluses plus 3 phosphates, PO4 3 minus, plus 1 OH minus. So KSP is equal to Ca2 plus to the 5th power times PO4 3 minus to the 3rd power times OH minus. So that's how we can write our equation and then the solubility product equation. So let's look back on this strontium chromate equation, and we were given a KSP, and we're told it's equal, again, like we looked at earlier, to strontium 2 plus times chromate 2 minus, and we're told it's equal to 3.6 times 10 to the negative 5th power at 25 degrees Celsius. Just like Kc and Kp and just all equilibrium constants, KSP has a fixed value at a given temperature. Okay, so it's very closely related to our other Kc and Kp. Okay, the product of the 2 ion concentrations at equilibrium will have this value regardless of the direction in which equilibrium is approached. Just like before, if we change the concentration of one, the equilibrium is going to shift so that it can get back to where it was. The equilibrium constant does not change unless the temperature changes. So there's a few ways we can establish a solubility equilibrium. We can add something that's sparingly soluble to water and stir it. And eventually the solution is going to become saturated with ions and reach its solubility point. If it becomes saturated, then we get that equilibrium between the dissolved ions and undissolved solid. And then we can calculate the solubility of a compound from its KSP value. And we call this solubility molar solubility because it's in terms of moles per liter, it's in molarity. But it's the molar solubility. So we say this is the concentration. We go the like most that can dissolve. We go a tiny even 0.00001 molar over this, and now we are starting to precipitate the solid out. We can also calculate KSP of a compound from its solubility instead of calculating solubility from KSP. There are a lot of different sources listing the solubility of sparingly soluble compounds. For instance, your book appendix has this in the back. Depending on the source, these solubility values can have a bunch of different units. Sometimes it's grams per 100 grams of solvent or grams per liter. So you have to make sure, though, that you do conversions to bring those units to molar solubility. So you bring it to molarity when you're using KSP. So let's go ahead and start doing a bunch of examples. I think I have 1, 2, 3, I have like 4, 5, 6. I have a lot of examples just for this one section. So we're told fluorite, CaF2, is a slightly soluble solid that dissolves with this equation. And then we're told that the concentration of Ca2+ in a saturated solution of CaF2 is 2.15 times 10 to the negative 4th molar. And we want to know what the solubility product of fluorite is. So we are told, we can use our stoichiometry as well. Okay, we're told that the concentration of CaF2 is equal to 2.15 times 10 to the negative, or I'm sorry, that's not CaF2, that's Ca2+. So we have a solution of CaF2, and that we're able to see that Ca2+ is 2.15 times 10 to the negative 4th molar. So we can use this to figure out the solubility product. So we need to figure out then the concentration of fluoride. I don't know why I did that. It's a big F. And the concentration of CaF2. And we're going to use our good old friend stoichiometry, because we know that fluoride, based off the stoichiometry, that if we have 2.15 times 10 to the negative 4th moles per liter, so this is moles of Ca2+ for every 1 liter of solution. We know that we have 2 moles of fluorine, or fluoride, for every 1 mole of calcium. So then that tells us that our concentration of fluoride is 4.30 times 10 to the negative 4th moles per liter, molar. We can do this basically same thing. Well, we don't even need to know CaF2. Sorry, I didn't even need that. And why don't we need it? Because it's a solid. It's not part of our KSP expression. Okay, KSP is equal to Ca2+ times F minus squared. So now we know our information. So KSP is equal to 2.15 times 10 to the negative 4th times fluoride, which is 4.30 times 10 to the negative 4th squared. So that gives us a KSP of 3.98 times 10 to the negative 11th power. All right, now we're going to do the opposite direction. We're told the KSP of copper 1 bromide, CuBr, is 6.3 times 10 to the negative 9th power. Calculate the molar solubility of copper bromide. So we need to go ahead and write our reaction. So this is going to be splitting up copper 1 bromide into copper 1 and bromide ion. So then we know that KSP is equal to Cu plus times Br minus. So let's go ahead and set up an ice table. Rewrite our reaction. I purposely write my reaction kind of big and wide for ice table so I have enough room for writing numbers. So for starters, nothing's going to happen in CuBr because this doesn't play any part in the equilibrium because it's a solid. So we know then that we started with 0 copper and 0 bromine at the start of this reaction. Since we're not told, we can go ahead and assume that all we started with was CuBr, but there's no concentration of it. It's a solid. We don't care. And we know that the Cu is going to increase by some x. Same with the Br, since from our stoichiometry, it's 1 to 1. So then we get that at equilibrium, they have a concentration of x. So we can go ahead and substitute these into the KSP equation. So KSP equals x times x, so x squared. And we know KSP is 6.3 times 10 to the negative 9th is equal to x squared. Take our square root, and we get that x is equal to 7.9 times 10 to the negative 5th molar. So that is the molar solubility of CuBr. Okay, and the reason we say that that is the molar solubility for CuBr is because it's a 1-to-1 ratio. We have 1 mole of CuBr for every 1 mole of copper. And in this case, X was our concentration for copper and for bromide. We didn't have to do any other finagling. If there was like a 2 in front of CuBr, then you would need to multiply it times 2. All right, the next one, the KSP of calcium hydroxide is 1.3 times 10 to the negative 6 power. Calculate the molar solubility of calcium hydroxide. All right, so calcium hydroxide, let's go ahead and write our equation. CaOH2 becomes Ca2 plus 2OH minus. And KSP is equal to Ca2 plus times OH minus squared. And we can set up our ice table. You know what, I could just use it here. We know there's nothing for calcium hydroxide, 0, 0 to start for calcium and for OH minus. So we know calcium is going to increase by some x, and OH then is going to be coming up by 2x since there's twice as much. So that equilibrium calcium is x and OH minus is 2x. So let's set up our KSP. KSP is equal then to x times 2x, which is 2x squared. So we have 1.3 times 10 to the negative 6th equals 2x squared. So I just substituted in our KSP we were given. X squared, then divide both sides by 2. Oops, I'm sorry. This is x times 2x squared, which is x times 4x squared, which is 4x cubed. Pardon me for that. So 4x cubed, there we go. So now let's divide both sides by 4. And we get that x cubed is equal to 1.3 times 10 to the negative 6 over 4. And we're going to take the cubed root. So make sure your calculator has this option. If it doesn't, then you would put 1.3 times 10 to the negative 6 over 4 and raise it to the 1/3 power. Same thing. So then you get that x is equal to 7.0 times 10 to the negative 3rd molar. Okay, so that's our concentration of calcium, right? And then we know that it's a 1-to-1 stoichiometric ratio between calcium and calcium hydroxide. So that means this is also equal to the molar solubility for calcium hydroxide. Again, if it was 2 calcium hydroxides, then you'd need to multiply it times 2. All right, next example. We're going to figure out KSP from gram solubility. Many of the pigments used by artists in oil-based paints are sparingly soluble in water. For example, the solubility of the artist pigment chrome yellow, PbCrO4, lead chromate, is 4.6 times 10 to the negative 6 grams per liter, and we want to figure out the solubility product. So let's write our equation first. PbCrO4 solid. This is going to be PbCrO4 is minus 1. No, it's 2 minus. So then this is Pb2 plus aqueous plus CrO4 2 minus aqueous. And then let's go ahead and convert our solubility that we're given in grams per liters. We need this in moles per liter. So we were told we have 4.6 times 10 to the negative 6 grams of PbCrO4 for every 1 liter of solution. And we need to turn that grams into moles. So we use good old molar mass. And we know there's 1 mole of PbCrO4 for every 323.2 grams of it. So you could either calculate this using periodic table molar masses or just look it up. And so then this gives us, so you can see our grams cancel, gives us moles per liter, which is molarity, 1.4 times 10 to the negative 8th molar. And then looking at the stoichiometry, we see it's a 1-to-1 ratio between PbCrO4 and the lead 2 plus and the chromate 2 minus. So that means that this is also the concentration of our lead 2 plus and our CrO4 2 minus. Okay, so now to find KSP equals Pb2 plus times CrO4 2 minus. So this is 1.4 times 10 to the negative 8th times 1.4 times 10 to the negative 8th. So we get that KSP then is 2.0 times 10 to the negative 16. So that's our solubility product. And this is just showing you some oil pigments, and you can see the chrome yellow, and this also has some Prussian blue, reddish orange colors, just vermilion and viridian as well. Another example. There's a lot of examples in this section, but this is the type of stuff where it's a lot easier to understand looking at examples than just putting letters on a board. So calomel, Hg2Cl2, is a compound composed of the diatomic ion of mercury 1, which is Hg2, 2+, and chloride ion, Cl-. Although most mercury compounds are now known to be poisonous, 18th century physicians used calomel as medication. Their patients rarely suffered any mercury poisoning from the treatments because calomel has a very low solubility, as suggested by its very small KSP. That should be an exponent. And then we're given the equation and KSP, and we want to find the molar solubility of Hg2Cl2. All right. So we already have our balanced equation, which is nice. We can see there's a 1-to-1 relationship between everything. So we know that the molar solubility of Hg2Cl2 will be, it's a 1-to-1 between Hg2Cl2 and Hg2, 2+. So that'll make our life easier. Let's go ahead and set up an ice table. Okay, Hg2, 2+, plus 2Cl-, ICE. We know nothing here. All right, so starting with 0 and 0 plus x, and we know Cl- is plus 2x. So we have x and 2x. We also can write our KSP is equal to Hg2 plus times Cl minus squared. So we can go ahead now and put in our x and 2x into that. So KSP equals x times 2x squared. I didn't forget it this time. So that's x times 4x squared, which is 4x cubed. And that is equal then, putting in our KSP, 1.1 times 10 to the negative 18th. So divide everything by 4 and take the cubed root. X is equal to the cubed root of 1.1 times 10 to the negative 18 over 4. And this gets you 6.5 times 10 to the negative 7 molar. And so that is going to go ahead and be our molar solubility of Hg2Cl2, since it's the same. But if we also wanted to know the concentration of Cl minus, that's going to be 2 times 6.5 times 10 to the negative 7. So that is equal to 1.3 times 10 to the negative 6th molar. But our main answer, all we cared about really is the molar solubility, which is the 6.5 times 10 to the negative 7. One example where some people have possibly experienced some slightly soluble compounds is good old barium swallows. I had to have one done when I was a kid, and it turned out to just be anxiety. I was like super afraid of this super mean lunch lady. Like, this lady was awful to us elementary school kids. She would yell and scream at us and make us eat our lunches super fast, and I was so scared of her I would throw up every day, or in the mornings too, because I was so scared. So I had to do a barium swallow to make sure that there wasn't something wrong with my stomach. And then recently I had surgery where I had to do a barium swallow also to make sure that my stomach was okay. It does not taste good. But basically, the reason that it works is because the barium compound isn't very soluble in water. When you drink it, it's able to highlight your stomach and your esophagus and everything going down. So there's better visual detail, as you can see in that picture there. So when I had my recent barium swallow thing, it was like a live x-ray. It was weird. They actually watched it go down. Now we can use KSP and QSP to predict if a sparingly soluble compound is going to precipitate. So remember, one thing you need to remember is that KSP only looks at ion concentrations. It doesn't look at their origin. So we can use that to our advantage to maybe introduce some more of a certain ion if we want to get it to precipitate out. If we get it so that our QSP is greater than K, then we would get precipitation and our reaction is proceeding in the reverse. If Q is less than KSP, there is not going to be precipitation and the reaction goes forward. So we can use what is called selective precipitation to remove individual ions from a solution. So recall that we can have equilibrium coming from either direction. So if we are starting with our reactants, we can add some solid compound to the water to get it to push forward more. Or if we're starting with just products, we can add the ions that we want to precipitate out to the water to get them to precipitate. So let's say we are mixing strontium nitrate and potassium chromate. We can use our KSP values to predict if we're going to get a precipitate or not. Okay, just like before, like I just talked about. Like I said, if we have a Q greater than KSP, we get a precipitate. If it's less than, then we have an unsaturated solution, so no precipitate. And if they're equal, we're saturated, and that means we're right where your precipitation is going to begin. So if we have a solution that has two cations in it, one way we can separate them is to add an anion that will form a precipitate with only one of them. So this is where solubility rules are also going to come into play. And then that precipitate we can remove by filtering it out. Because now it's out of solution, it's a solid, we can filter it and separate it. And the other cation stays in the filtrate, which is the liquid portion that would pass right through the filter. And so this is called selective precipitation, and we can use this as a method of purification. So we can remove some type of impurity by precipitating it out, and then everything else stays in our water and it's better. An example, a solution of magnesium and sodium ions. Most sodium compounds are soluble in water. But magnesium, let's say we want to pull that out, it can form a compound with carbonate, which is only sparingly soluble, okay? So we can add some type of carbonate to our solution, which is going to grab onto the magnesium and precipitate it out. We can also have a solution that has magnesium and barium ions at the same concentration, and we can slowly add carbonate ions. And even though they both have low KSPs, they still have a big difference in solubility. So we can use that to separate the cations. And you can sometimes be able to predict what's going to precipitate first. You could probably, looking at these KSPs, assume that the barium is going to precipitate first. But we can't always just use KSP to answer this question. So when can it be used by itself to predict what's going to precipitate first? The first criteria that must be met is that both ions to be separated have to be at the same initial concentration. So from this example of barium and magnesium, we would have to have the same concentration of barium and the same concentration of magnesium. So they would have to be equal. And they have to have the same cation to anion ratio, meaning 1 to 1, 1 to 2, 2 to 2, 2 to 3, but would have to be the same. If these criteria are not met, then you have to do calculations to figure out what is going to precipitate out first. One place where selective precipitation is used is in wastewater facilities. So this is an aerial shot of one. These are all over the place. One of my good friends from grad school actually did his dissertation work on, I did a lot of work on wastewater facilities and the particulate matter from bubbles bursting in them and potential health effects. Really cool stuff that he did. So these are used to remove contaminants from wastewater so that we can use it again. Usually this is called like potable water. When they say, oh, careful, it might be dirty, it's gone through a wastewater treatment, it's probably fine. So let's look at an example. The first step in the precipitation of magnesium metal is the precipitation of magnesium hydroxide from seawater by the addition of calcium hydroxide, a readily available, inexpensive source of OH-. And so we're given this reaction there. The concentrations of Mg2+ in seawater is that. Will it precipitate when enough calcium hydroxide is added to give an OH- of 0.0010 molar? So let's start by writing our Q equation. So we know that QSP is equal to Mg2+ times OH- squared. So based off of these values we're given here, we have a calculation of, or a concentration of magnesium, and we have one of OH. So QSP is going to be equal to 0.0537 times 0.0010 squared. And this gives us 5.4 times 10 to the negative 8th. And this is bigger than KSP. Okay, 8.9 times 10 to the 12th. That's a lot bigger. So that means that the reverse reaction is going to be favored. And so we're going to precipitate magnesium hydroxide out until we get back to equilibrium. So yes, we get precipitate. Another example, does silver chloride precipitate when equal volumes of a 2.0 times 10 to the negative 4 molar solution of silver nitrate and a 2.0 times 10 to the negative 4th molar solution of sodium chloride are mixed? So let's look at some of this. So the first thing we should think of is the silver chloride is what we're looking for here. So since we want silver chloride, that's AgCl. The equilibrium for this is going to be Ag plus plus Cl minus. Okay, and if we were to use the appendix, we find that KSP for AgCl is equal to 1.6 times 10 to the negative 10th power. And so this is in the appendix, appendix 3. So KSP, or I'm sorry, AgCl will precipitate if we get a Q greater than KSP. One thing we need to keep in mind is that when we combine these two solutions, the volume is going to double because we're adding equal volumes of these two solutions. Okay, so, if I've got a test tube here and I start with one thing and I add another, boom, x plus x equals 2x. So now that means that our concentration will go down by half because now we've doubled the volume. So now your 2.0 times 10 to the negative fourth, that's moles per 2 liters now. So now our concentration of silver plus is equal to the concentration of silver nitrate. And that is equal to 1/2 times 2 times 10 to the negative fourth, which equals 1 times 10 to the negative fourth molar. And the same can be said for the chloride ion, which is the same as the concentration of sodium chloride. And then this is going to be 1/2, same thing, 2 times 10 to the negative fourth, which is 1 times 10 to the negative fourth. So now our Q is equal to Ag plus times Cl minus. So that's 1.0 times 10 to the negative fourth times 1.0 times 10 to the negative fourth. And Q is equal to 1.0 times 10 to the negative 8th, which is greater than the KSP of silver chloride. So yes, we're going to get a precipitate. Hopefully this is making sense so far. As usual, though, please remember you guys can ask me if you have any questions. Another example, example 15.9, precipitation of calcium oxalate. Blood will not clot if calcium ions are removed from its plasma. Some blood collection tubes contain salts of the oxalate ion, C2O4 2- for this purpose. At sufficiently high concentrations, the calcium and oxalate ions form solid calcium oxalate monohydrate. The concentration of calcium 2+ in a sample of blood serum is 2.2 times 10 to the negative third molar. What concentration of the oxalate ion must be established before calcium oxalate monohydrate begins to precipitate? So this is kind of cool because I actually just had a blood draw a couple days ago. So if you notice when they take your blood, there's some tubes that have some stuff at the bottom, and the phlebotomist has to make sure they use the correct tube to put your blood in because, for instance, they may not want the blood to clot. So they need to make sure they've got the one that has oxalate salts so it keeps it from clotting by removing the calcium ions. So the first thing we need to write is our equilibrium expression. We're going to ignore the monohydrate part of that. That really doesn't affect anything here. So calcium oxalate in equilibrium with Ca2+ plus C2O4-. So our QSP is equal to Ca2+ times C2O4 2-. And if you were to look up from your appendix, KSP for the calcium oxalate is equal to 1.96 times 10 to the negative 8th power. So basically here, what we're looking for is we're looking for our equilibrium point. Because at equilibrium, QSP is equal to KSP, and this is going to be right where precipitation starts. So again, that's Ca2 plus times C2O4 2 minus. And we do not know what our oxalate ion concentration is. We know calcium and we know KSP. Okay, so we know then that C2O4 is going to equal KSP divided by our concentration of Ca2 plus. So that is 1.96 times 10 to the negative 8th power divided by 2.2 times 10 to the negative 3rd molar. And this gives us 8.9 times 10 to the negative 6 molar. I know the units don't really work here, just, yeah, take my advice for it. So that is the concentration of the oxalate ion that we need to start the precipitation of calcium oxalate under these conditions. So this is a type of question that gives you a whole lot of information, and it kind of feels very overwhelming. So the best thing to do is to break it apart and really focus on that last question, the concentration right before precipitation. So that tells us the concentration at equilibrium. So that's when QSP equals KSP. And this is just a picture of some of those tubes. Notice I skipped example 15.10. We'll either go over that with chapter 14 examples or later chapter 15 examples because it incorporates stuff from chapter 14 that we have not learned yet. All right, so example 1511, a precipitation of silver halides. We're told the solution containing 0.00010 moles of potassium bromide and 0.10 moles of potassium chloride per liter. We add silver nitrate gradually to the solution, and we want to know what forms first, solid silver bromide or silver chloride. So this is one of those questions that we cannot just guess based off of the KSPs. So let's go ahead and first write our reactions that are happening. So we have AgCl solid becoming Ag plus and Cl minus. And it has a KSP value of 1.6 times 10 to the negative 10th. And then our other one is AgBr. And this one's KSP is equal to 5.0 times 10 to the negative 13th power. So if this had equal concentrations of chloride and bromide, then the salt with the smaller KSP, which is the silver bromide, would precipitate first, but they're not equal. So we have to do math. All right. So the one that gives us the lower, so we're going to have to go and calculate the silver plus concentration and figure out where everything starts. The salt that forms at the lower silver concentration is the one that precipitates first. Ugh, sometimes I have a hard time saying precipitate. It's one of my favorite words too. Okay, so let's start with silver bromide, AgBr. So we know it precipitates when KSP equals KSP. Right, so that means we have the concentration of silver times the concentration of Br minus And we know our concentration of Br, because we get that from the KBr. And we do not know silver. So the concentration of silver ion is equal to KSP over bromide. So that is equal to 5.0 times 10 to the negative 13th power divided by the concentration of bromide, which is 0.00010 molar. And that gives us 5.0 times 10 to the negative 9th molar. Okay, so that's when the silver bromide is going to begin to precipitate. So when the silver is at 5 times 10 to the negative 9th molar. Now we need to do this for AgCl. Same thing, QSP needs to equal KSP, which is Ag plus times Cl minus. And the concentration of silver is equal to KSP divided by Cl minus, which this is equal to 1.6 times 10 to the negative 10th divided by the concentration of Cl, which is 0.10 molar. And this gives us 1.6 times 10 to the negative 9th molar for silver. So that means it begins to precipitate when we have a concentration of 1.6 times 10 to the negative 9th molar. So if we look at this, the concentration, this guy is actually lower than bromide. So in this case, AgCl is going to precipitate first because you need less silver for this one than you do for the bromide. So you really have to do the math to make sure. All right, so what would you think would happen if we had some barium sulfate in pure water and then we instead put it into 0.10 molar sodium sulfate? So so thinking of what we were just talking about now, we just added more sulfate ion. So that should then make it precipitate out more because we're adding more of one of those products. So remember Le Chatelier's principle from chapter 13. The presence of that common ion is going to drive the equilibrium to the left. So you can add common ions to reduce solubility. The source of the ions does not matter, like we were just looking at with the selective precipitation. So this is called the common ion effect. Now, what if we took it from water and put it in sodium chloride? Nothing will happen with its equilibrium. There's not going to be a change because there is no common ion. So we can look at some examples. What is the effect on the amount of solid magnesium hydroxide and concentrations of Mg2 plus and OH minus when each of the following are added to a saturated solution of MgOH2? If it helps, we can go ahead and write the reaction. Okay, so let's say we add some MgCl2. So this is going to increase the concentration of magnesium 2 plus, which means equilibrium is going to shift to the left. So that means we're going to get a precipitate, more precipitate. Adding KOH, we're again adding a common ion. So we're increasing the amount of OH minus. So again, we are going to shift our equilibrium left and precipitate out more magnesium hydroxide. NaNO3, we don't have any sodium or nitrate ions here, so nothing. So this is not going to have an effect because there is no common ion here. And the last one, adding more MgOH2, that's a solid. And what do solids do to our K or QSP equation? Nothing. These do not affect the equilibrium. So it's just adding undissolved magnesium hydroxide. All right. I believe this is the last example. We're almost there. So this is an example about the common ion effect. We want to calculate the molar solubility of cadmium sulfide in a 0.010 molar solution of cadmium bromide. And then we're told the KSP of cadmium sulfide is 1.0 times 10 to the negative 28th. That's a tiny number. So let's go ahead and set up an ice table to start. CDS, solid. Then we have CD2 plus aqueous plus S2 minus aqueous. ICE. Nothing for the solid. Now, we know that we're starting here, though, with 0.010 molar cadmium because this is a solution of cadmium bromide. So we don't have any sulfide to start with. Okay, so we're adding cadmium sulfide to cadmium bromide. So that means that we're starting with 0.010 molar of cadmium, of the cadmium 2 plus from the cadmium bromide. Okay. Since it's a product, both of these, though, the amounts of them are going to increase by some x. So at equilibrium, we have 0.010 plus x for the cadmium 2 plus, and then just x for our sulfide. So our KSP equation is equal to CD2 plus times S2 minus. So now we can go ahead and set this up. KSP is equal to 0.010 plus x times x. And then that gives us 0.010x plus x squared. And that is equal to 1.0 times 10 to the negative 28th for KSP. Oh, you know what? Hold on. Let's go ahead and use a shortcut. So we, based off of the KSP that we're given with how small this is, the change in the amount of x is going to be super, super, super small. So we can go ahead and assume that x is much less greater, or less than, sorry, 0.010. So then we can just get rid of this plus x and assume that it's not enough to really change this concentration. So then that gives us 0.010 times x is equal to KSP, which is 1.0 times 10 to the negative 28th. Okay, super tiny KSP is the only reason we're able to do that. Divide both sides by 0.010. And we get that x is equal to 1.0 times 10 to the negative 26 molar. It's so cute. It's so little. So that's our molar solubility of the cadmium sulfide because it's a 1-to-1 with the sulfide. So this is basically telling us the concentration of S2 minus, which is a 1-to-1 ratio with cadmium sulfide. So we can go ahead and say that that is what our value is. And it's pretty much the same also as the CD2 plus because it's so, that x is so much smaller than 0.010. So there we go. I believe that does it for this chapter. Well, for that section. And then chapter 13. So you guys are probably really tired of the letters K and Q. We'll be looking more at them and other stuff uh, with the next chapter. But this is a 2-week chapter, I believe. So as usual, if you guys have any questions, please, please, please text me, email me, call me, whatever it is that you may want to do to contact me, and I will do everything I can to answer those questions. I hope you all are staying safe and sane and taking care of yourselves, and I will see you all soon.